Good afternoon, Professor and everyone. My name is Prohim, a master candidate from Mobile Computing and Networking Lab, who is under the supervision of Professor Kim Suk Hon in Software Conversion Department, Songchon University. Today, I would like to present about my project, namely Efficient Network Slicing Scheme for handling massive healthcare Internet of Things communication. To significantly describe this topic in detail, this is our content table, which starting from the introduction of 5G based healthcare Internet of Things that discuss about the conventional architecture, challenging and possible problem in nowadays scenario. And next, I rest about the main objective of our approach to handle the existing drawback. In section 3, the efficient network slicing scheme is described in terms of algorithm flow and principal concept. Then I describe about the development plan for this approach, and finally the conclusion is given in section 5. So let's get started with the introduction of 5G based healthcare Internet of Things. In real environment, among various technology, 5G communication is expected to enable the transmission of smart healthcare application with ultra low latency, ultra high reliability, and high throughput. In this figure, the illustration of conventional approach is briefly described, which consists of end-to-end communication flow from source to destination. However, the end device layer obtains heterogeneous IoT device in terms of functionality such as sensing device, actuating device, data collecting, data carrying, and general IoT device. And in those IoT device, there are various types of sensing, including electronic-based, software-based, or human-based. So depend on the overall complexity of this IoT device, the management and orchestration of massive communication traffic in network environment is very challenging to overcome. Additionally, the control layer nowadays consisting of non-intelligent configuration, which degrade the scheduling or fault intolerant control of the application, especially healthcare system. More importantly, the congestion could possibly occur when the traffic flow reach the maximum capability of communication and computation resource, especially in backhaul network environment during the peak hour interval. With all these mentioned issues, the quality of experience of healthcare service can be vulnerable and does not achieve a certified level or even affect the patient's life situation if the packet drop ratio is getting higher. So what are the main objective or goal should we mainly consider? In the next section, the proposed approach main objective is described, which consists of a flexible control to slide each service along with an intelligent auto configuration and classification, prioritization, and extra serving resource allocation to handle the healthcare Internet of Things density. In the 5G service layer, the application criticality is required to be well classified between mission critical and non-mission critical. For example, in mission critical, there are some application systems such as urgent healthcare wellness system, remote patient monitoring system, medication tracking, remote surgery, and so on, which require a high performance metric configuration. And the non-mission critical such as background or interactive application, it can be delayed without seriously affect the user. Significantly, the main objective is to output the visualized slicing in 5G network slicing layer by processing the network function visualization, software-defined networking paradigm, and hypervisor-based function. And how can we apply those enabler technology in our project is will be presented in the next section, which is efficient network slicing scheme. In this figure, the proposed approach is converged by applying an algorithm model, namely deep neural network, to activate an intelligent network function visualization in SDN controller. The SDN architecture is applied to decouple the application plan, control plan, and user plan by using a standard protocol called as OpenFlow on southbound communication interface, and or we call it control data plan interface, and using representational state transfer application programming interface to interact between control plan and application plan. Furthermore, OpenFlow protocol collect the healthcare Internet of Things node information through OpenFlow vSwitch as the cluster head and store it in the visualize server to process the deep neural network model. More importantly, multiple mobile edge computing server is proposed to serve the control plane computation and pick our mission critical application. So this is the overall flow chart of our scheme, which technically start from the healthcare Internet of Things training data collection, and then the data are being processed by deep neural network with multiple conditions as hidden layer function, and it is imported from application service requirement, and then the algorithm flow to inspect the deep healthcare packet, which is required to identify the related feature in communication network. Next, the classification of packet flow is initialized by applying Adam function as the activation algorithm and ReLU method as the solver algorithm. In the next stage, the implementation of high-dimensional state space and action space is proposed in order to improve the model for handling the variety of multi-dimensional features from our dataset. After the model training is complete, the general communication flow is processed for testing the fitness of the model parallelism. If the data does not fit, the data processing with deep neural network is being executed again. But if the data fit, the SDN-oriented architecture will be implemented, and then the real SDN controller is orchestrated and capture the quality of service performance by using IPOP package. Next, if the quality of service performance, such as packet drop ratio, delay, or jitter of the model is satisfied, the hypervisor-based function will be configured accordingly. But if the performance is not satisfied, the SDN controller required to update the flow table or priority condition over again. After that, the visualized network slicing configuration is obtained and evaluated until the output is satisfied. When it does, the simulation topology is saved and the proposed scheme is finalized. In the next section, which is section 4, the development plan is briefly illustrated and being separated into 4 main stages, including stage 1, we focus on the surrounding environment of 5G-based healthcare Internet of Things network, the various type of critical application and feature extraction from network perspective. And for stage 2, we focus mainly on the deep neural network part by setting the training data, build the model, and evaluation on the accuracy matrix. For the third stage, MiniNet simulator is used to activate the SDN-oriented architecture and utilize your operating system for controller, OpenFlow protocol for controlling flow table, and RESTful API for synchronously interact with healthcare application system. For the final stage, the network slicing is configured accordingly based on the SDN management status and deep neural network recommendation. Last but not least, the performance evaluation of the proposed scheme will be analyzed over and over to minimize the failure and maximize the reliability. Moving on to the final section of my presentation conclusion, which I want to summarize the main end goal of this project. The proposed scheme is expected to ensure the 5G smart healthcare environment with high reliability, ultra low latency in millisecond, communication and computation resource efficiency, and energy efficiency for IoT device. Moreover, to ensure the prioritization of mission critical application in healthcare and handle all the possible congestion by attaching extra serving server and also activate adaptive control and intelligent decision output by converging the communication network with deep neural network paradigm. Thank you so much for your paying attention, and if there are any other questions, you can contact by my email and phone number. Thank you very much. Oh, finish. Oh.